Hi everyone, welcome to the second video for Module 10, where we're talking about dealing with non-independent residuals. In the video today, we want to walk through a situation in which we have non-independence and nested designs. So we're going to be talking about the example from the textbook. In class, we've been talking about using the within subject contrasts, right, and how to calculate those different codes or W's that the textbook uses. In the video today, I'm going to show you a little bit more conceptually about what those W's represent and kind of an alternative way of approaching the problem that presents us with the same answer. But as always, we're trying to understand how to partition the variance within our dependent variable so that we can have independent error terms in our analysis. So we're dealing with non-independence in a nested sample. So again, this is the example from the textbook where we had students in either competitive groups or non-competitive groups, and each individual student was assigned to a group. So in group 1, we had student 1, right? Group 2 had a different student 1, group 3 had a different student 1, right? So you could really think of these as students 1, 2, and 3, but they're the first student in each group, right? And each group is made up of 3 students, but the issue is these 3 students are all in the same group and therefore more similar to each other than the students who are in this group and the students who are in this group. So in this situation, we have students nested within groups because we have different students in our different groups. If we had the same student in 3 different conditions, these factors would be crossed, but because we have different students in each of the different groups, these factors are nested. And this gives us different ways of looking at the data, right? One is at the subject level, where we can see each score for each subject in each group. One is at the group level, where we can see the mean of each group. And then we can look at this at the condition level, right? So we have groups within each condition. And if we want to understand the effect of competition, right, we have to understand at what level is it appropriate to look at our data. And if we look at it at the subject level, we think then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 data points in each group, or 18 data points total. But the issue is we don't actually have 18 independent observations. We only have 6 independent observations. We have group 1, group 2, and group 3. Group 4, Group 5, and Group 6. So we actually have to reduce our data down to the group level in order to get means that will then lead to reliable residuals when we actually go to analyze our data. So in the example today, I want to show you how we're going to fill in this ANOVA table from the book, right? By taking different levels of aggregation, by averaging our data together, right, in different ways, and partitioning the variance, right? Because remember, this is an analysis of variance. We want to understand how do our data vary by condition. And in order to do that, we're going to have to partition our data into sources of between group variance, within group variance, and total variance in order to properly ask this question, how much variance is explained by the effect of condition? So the first thing that we can do is get a calculation of the total variance. So the total variance, or the total sum of squared errors, is going to result from taking each individual observation minus the mean of means. So we take for our 18 different scores, right, each YHIJ, right, so for the score for each person in each group, in each condition, we are going to subtract off the mean of means, which is 6.5, and that will give us the sum of squared errors of 28.50 with 17 degrees of freedom, because we do have 18 different scores here minus the grand mean, which we are estimating, or I should say the mean of means, which we are estimating. So we have 17 degrees of freedom. Next, what we're going to do is we're going to take each individual score within a group, and then we're going to subtract it away from its group mean. So this is going to tell us about the total variation within groups. So of this 28.53 squared errors, right, how much is due to variation within our groups? So by calculating the total sum of squared errors within each group, what we can do is take each person's score, subtract off the average for that group, and we can tell how much of an error that person is relative to their group. So for person 1 in group 1, they're right at their group mean, so their residual would be 0. For person 2 in group 1, they are 1 point above their group mean, so their residual would be 1. And for person 3 in group 1, they're 1 point below the group mean, right? So they would have a -1 residual. If we added all of those squared errors together, we end up with 5.33, and then we're going to have 12 degrees of freedom for this factor, because we have our 18 minus 1, 2, 3, 4, 5, 6 different group means. So within group variation is 5.33 with 12 degrees of freedom. Next, we can calculate the total variation between groups, because we want to know how much do the groups vary from each other, because that's actually what's going to allow us to then make an appropriate calculation for the effective condition, right? So we have to know how do the groups differ, so we can take the difference between each group mean minus the mean of means. So you take 8 minus 6.5, square it, 6.33 minus 6.5, square it, 7.6 minus 7.67 minus 6.5, and square it, and so on. And by adding all of those squared deviations together, we find that we have 23.17. We could also get this by subtracting from our total our within group variation of 5.33, and that would leave us in the same place. But just doing that subtraction doesn't really tell you exactly what we're calculating, right? What we're trying to calculate here is how much do the groups vary around the grand mean. How different are these groups from each other? And we have 23.17 as our total between group variation, and we have 5 degrees of freedom here because we have 6 independent observations minus the 1 parameter for the grand mean. Now, our calculations are going to get a little bit trickier here, but this is why it's important to actually calculate these different sums of squared errors and partition out our variance. So in order to calculate the error between groups, what we need to do is take each individual score, right, or the estimated value for each person, the estimated value for each person in each group, minus the actual score for each person in each group, and get those squared errors, and subtract out the sum of squared errors where we take each score, right, for each person minus the average for each group. So what we're going to be left with then, right, is something akin to the classic sum of squared errors of our residuals, right? So this first part of the equation, where we're taking the difference between the model's prediction and each score and then squaring it, that's equivalent to the sums of squared errors for model A that we've calculated in previous regression equations. However, we now have to take out the within group sum of squared errors from that calculation. So we take this sums of squared errors, which is equivalent to SSEA, and we subtract off the within group variation to then leave us with 10.67 and 4 degrees of freedom. So our error between groups after, the sum of squared errors for the residuals between groups is 10.67. And this is the sum of squared errors then that we can use to compare to the effective condition and actually calculate an F statistic and then make an inference about do we have a significant effect of instruction on our different groups. So finally, in order to calculate the appropriate effect for condition, what we're going to need to do is take the predicted value for in each person, in each group, at each different type of instruction, minus the grand mean, right? If we were to just estimate the mean of means for everyone and calculate those sum of squared errors. So what we're going to have then, right, is 7.33 is going to be our estimate for every person in every group who received the competitive instructions. So for this person, the model's prediction would be 7.33. For this person, it would be 7.33. For this person, it would be 7.33, right? And then for everyone on this side, it's going to be 5.67. So for this person, it would be 5.67. For this person, it would be 5.67. For this person, it would be 5.67. And we're going to take each of those deviations from the predicted values away from the mean of means. And that's going to give us then our total sum of squared errors for the effective condition, right? Or this is the sum of squared errors reduced. So this is the total variation that we've explained of the between group variation, right, is 12.5. So we explained 12.5 squared errors by making different predictions for our two conditions. And that leaves us with 10.67 squared errors left over. So this is the sum of squared errors reduced, and this is the sum of squared errors of the errors, or the sum of squared errors of the residuals that we're used to seeing in previous examples. The only new wrinkle here is that we've had to subtract out this variation within group to account for the fact that scores from individual groups are going to be more like each other than they are different. So now we have everything that we need in order to calculate the mean squared error reduced and the mean squared error of the error term, which will then allow us to calculate an F observed. So this F observed we can actually calculate fairly because we're not going to have residuals that have statistical dependence. So because we've removed that within group variation from our calculation. And this highlights the magic of using sums of squares. If you remember back to previous examples, we talked about situations in which we want to use the sum of squared errors compared to using something like absolute errors. And we said that both the sum of squared errors and absolute errors will get rid of signs in our error term. So positive and negative errors don't cancel out. But we also said there were some mathematical reasons to prefer the sum of squared errors. And this is what we mean when we say there are mathematical reasons to prefer the sum of squared errors. You can think about each of these blue dots as a data point, and they all fan out around some mean observation. So this is our grand mean, and each of these dots is a data point. Now, we can calculate the actual deviation of each of these errors away from this grand mean, but we can also account for the fact that some of these errors are statistically related to each other, and they might actually be grouped, right? So now these dots all go together in one group, these dots all go together in one group, and we have 4 total groups. So we have group means around our grand mean. So now we actually, rather than calculating the distance between each of these dots and the grand mean, we can calculate the distance between each of these observations and their group mean. So that would look something like this, where we can calculate the sum of squared errors within each group. But then we have groups, and these groups then have a distance from the grand mean, right? And we can calculate the distance between each of these nested groups and the grand mean. So in order to do that, right, let's say if these are, we have these different treatment effects, right, within these different groups, we can do a separate calculation, and now we can properly account for the fact that we actually have 4 independent groups that are contributing to this average, rather than several different data points that are contributing to this average. So the beauty of the sum of squares is that we can partition this variance, and the sum of the variation within groups plus the sum of variation relative to the original, from the groups relative to the mean, is going to be equal to the total sum of squared errors.